Name's Josh Pritchard. Glad to be here with you today. I'm here to talk to you about some exciting things that we've been doing with our application called Nav Portal. This was born out of the idea of the core is a lot of times project funded. Therefore, our products end up and software end up inherently stovepipe just because of that, right? We're very much mission focused. And because of that, you end up with these silos, right? And trying to bring all that data together collectively just doesn't always work. Dr. Ned Mitchell at ERDIC, the acronym there on the screen, he is the one that's been sort of driving this project to life. We've been working I've been at the core for 4 years now, and been working on and off through contract gaps on this project for about 2 years, with just a team of about 4 developers to see what you're going to see today. We were actually the proud recipients of the 2021 Elastic Innovation Award, which we're very proud of. So yeah, you'd have to be, in order to fully understand the vast amounts of data that the Corps of Engineers has through our navigation infrastructure, you'd have to be an expert in SQL, Oracle, Elastic, Kibana, ArcGIS Pro, AutoCAD, right? You'd have to figure out how to wire all that data together, and the goal of Nav Portal was to kind of get rid of that barrier, right? To look at your data in a seamless viewer and be able to serve out APIs that would serve other projects throughout the core in a meaningful and intuitive way. So what are we building here? What is this navigation system? The goal is to provide safe, reliable, efficient, and environmentally sustainable transport systems for vessel traffic, right? This includes, but is not limited to, national security needs, commerce, and recreation. You can see that from some of these statistics, they may be a little hard to read, but just about half of the consumer goods that come to your doorstep in the form of those little brown boxes are not by happenstance. They come through this framework. So, you know, unlike a road that's maybe not paved very well, where you have to, you know, slow down in your car, take a detour, semis can't go through that area. If our channels are not maintained, then import and exports do not happen. You eliminate entire classes of cargo ships, the deep drafters that are bringing in everybody's flat screen TVs, right? And exporting goods and services to other countries as well. So that's huge implications here, right? Some more of these statistics. You can see that we have over 12,000 miles of inland and intercoastal waterways that we maintain. Also 13,000 miles of coastal channels at over 400 ports in the US. On average, since 2010, we have removed about 220 million cubic yards annually of material from these channels, right? So if we don't, you know, a lot of these bays and estuaries are shallow by their just natural geography. So we actually have to go in there and remove that material to be able to make sure that these ships can go in and out of these channels just fine. So that 220 million cubic yards, that's like 14 million dump truckloads of material that come out of these channels every year. So that's a significant amount of material at a cost of about $2.5 billion, right? So that's all of our money, right? The taxpayers. So even just a small innovations that we find in this space can yield tremendous savings to us as tax-paying citizens. Here we can see some of the problems that we encountered with Nav Portal. So within a large organization like USACE, we have to be able to understand our geospatial data, and sometimes a point is too specific, right? It's very hard to compare a lot of point data to each other because they really, you know, if you take that decimal point precision out far enough, we've yet to collect a survey point on top of each other. So how do we study that object through time? Individual pings from surveys collected over the last decade can be too unique for that. So unless we have something that we can associate these points to, then it really doesn't make sense to compare these objects through time. Also, we have a lot more data than just survey data, right? We have AIS data, decades worth, data coming in from the Coast Guard, and here you can see this is actually one of our surveys rendered in Kibana, so you can actually see sand waves and stuff associated with that. This actually looks like a raster, like you're looking at some sort of TIFF file or something. This is vector objects being rendered in the browser very quickly. Quick poll of the audience, actually. Have any of you ever heard of a global gridding system? Okay, couple handshakes, couple hands. Had anybody taken Uber or Lyft or anything like that from the airport? All right, all these hands, those are, y'all have used the global grid system this week. So this system was developed by Uber, I believe it's been 5-6 years ago now. They worked in conjunction with Elasticsearch to develop the system. And what they were using it for was pairing a driver to a passenger and eventually to a destination. Well, the core, we also have very similar needs, right? Where we're pairing a dredge vessel and survey vessels to a channel, and then eventually we need to take that material and put it somewhere, right? Sometimes we put them in what we call placement areas, which may be offshore placement areas where the material's just dispersed because that's the cheapest means to dispose of that material. Other times we can study the grain size of our local beaches and projects that are going on to see if there's any beneficial use for that sediment somewhere else, right, to make the most of our money. Sometimes that may cost a little bit more, but in the long run, like if we got to go, replenish that sediment from somewhere else, then we're actually saving money, right? So Nav Portal can be used to sort of bring together that to optimize that spending. So actually on this slide again, you can actually see some of the nesting associated with this Uber H3 is what we ended up going with. So you can see each bin has 7 children bins, right, associated with them. And there's 15 different resolutions ranging from like the size of continents to about the size of a kitchen tile, like 1 square foot, right, where you aggregate this stuff. So if you're aggregating ants in an ant bed or something, that would be kind of helpful to that resolution. LiDAR data is another one that would be very dense to aggregate to that level. It's kind of a funny side note. It's like whenever you start processing your data into these hex bins, like you start seeing them everywhere, right? It's like you go to your favorite restaurant and you notice stuff that you never really see before on the floor. You're like, what is this? Like, why am I thinking this? My wife was picking out at a hardware store. We were picking out like fax flashes, right? And the 2 options were like rectangles and hex bins, right? It's like, which one am I going to use? Like, I'd rather not think about work when I'm sitting there eating dinner, right? So anyway, went with the rectangles. So. To the left image here is an example of what you would see with single beam survey points collected by our districts, right? They're the local experts, boots on the ground, the people that move dirt, right? And sand and whatever else ends up in our channels. I'll let your imagination run wild. But essentially, turns out outlining points aren't as simple as it seems. So we let them take care of that based on all the different collection methods of these surveys. And they end up creating what's called a TIN for us, which is just an outline of these points. And then it has some metrics associated with those, with interpolating those points onto like a surface, right? And then here I've purposely blown up the bin so you could actually see them on a projector. But you can actually see what we do is we take the minimum depths that we find in this tin, and then we turn them into these hex bins, right? And each of these hex bins have a globally unique object ID that we study through time. So, Frank, Bob, all these things have names that we study through time. So we get an idea of some different metrics that are occurring in our channels. So here's another visualization that we've been quite happy with. This is just a couple of surveys in Detroit. It's actually 3 different surveys collected in Detroit. Won't get into too much of the specifics about the difference in single beam and multi-beam, but essentially single beam is just a row of points, right, collected at various transects along the channel. And then multi-beam survey is, as you can see, it's just a bunch of dense points stacked on top of each other, right? And then we have a lower density multi-beam survey at the top. And what you can see, after we run it through this pipeline that we have, it outputs, we're using the resolution 13 hex bin size to sort of take the minimum depth found in each of these little micro areas that we call hex bins, right? And then we can study that particular object through time, regardless of what the survey type is, right? So that becomes very important to our field practitioners, so that we can, inform the local and district offices all the way up to headquarters on where problems may be occurring in our channels before they actually occur, right? Like, we can predict that. So here's an example of looking at data, at different data through the same lens, right? So to the left, we're looking at one of our hydrographic surveys. To the right, we're looking at vessel densities, right, by MMSI, which is the unique number in that world, right? So if you think of, I guess a way to put of this is, if you think of channel depths as the supply, the vessel traffic in the maintained waterways is the demand, right? It's what's driving the work to be done. Where do we need to move material? How do we do it in an efficient way? How do we link all this stuff together? Same problems that Uber encountered whenever they originally developed this system. So, we collect a lot of data from the Coast Guard. We backfill with marine cadastre. We've got like a decade's worth of AIS data in this system. Here we're looking at the same data at different resolutions. And you remember that child-parent relationship that I talked about with the bins. Oh, that's kind of interesting. But this relationship is, this isn't officially supported lingo within the system or anything, but I guess the resolution 13 to the left is what we process our surveys to. So you can see that when you're looking at this data from, at this scale, you can barely even tell that they're hex bins, right? They're so small. So that's why it gives you that raster-like feel and look, right? You can instantly, in Kibana or any other custom application, you can just window a box around these points and update your table and get those statistics for these bins on the fly. And you can tell by this particular slide, just changing the resolution yields a completely different result. Like, if you look at this resolution 13 on the left, and you see, well, there's a lot of vessels at that dock. Well, it's just a bunch of vessels parked there just pinging constantly, right, on the dock. When we increase the size of that bin, it shows us where the traffic really is, right? Because it's circling more points in a geography to highlight that, hey, actually vessels are out here, right? Depending on what your use case is, you pick the resolution you want. So yeah, let's see. Okay, here's another visual in Kibana. I know it's going to be kind of hard to see the search terms up top on the projectors, but this is actually one of the most dredged places in the world. This is Southwest Pass, Louisiana. This is the mouth of the Mississippi River. If you look at imagery in that area, in fact, you can see it a little bit there, just to the bottom of that legend, but there's always a vessel there draining in Southwest Pass. This is the most dredged and surveyed place in the world, but in this example in Kibana, we've got the calendar set to the last 2 years, and we've got a filter up in the top using Kibana's query language to search for what we call positive volume. And what that means is that we are doing a search across these bins to figure out where we have sediment. Because we're turning points into little areas, we can then do that high school math. Everybody, questions why they even took high school math. We can just do some basic math on that to figure out what the volume is based on the amount of the depth that this channel is supposed to be at, right? So as soon as we ingest a survey, we process it into the surface and then it can determine or infer what a particular amount of volume would be in that channel. This is very useful information, and you can see over the past 2 years, this is the aggregation result of all of that data. The white lines you see here are the sort of the patchwork nature of our hydrographic survey collection. So we have 200 or 300, actually we have more than 300 surveys collected in this one area in this 2-year time span, right? And because of the query term that we put on there of we want to show positive volumes, we're actually showing you where there is mud in our channel. Our channel is outlined by these black boundaries, right? So you can see just a little bit of encroachment along the edges where, over the past 2 years, where there have been problem spots in the past, right? So those are areas where we actually have to send out dredges and maintain that. So this is actually showing that we're maintaining this particular waterway very well, because in a 2-year time span, we've had very little encroachment into our channels, right? And then at the bottom right were all the different aggregation types that you can perform against these bins: min, max, mean, all that stuff on each bin. So here's an example of what we do with our, this red line sort of represents where we're at in time now. And say we collected a survey last November. It was deemed that it needed some work, right? One bin alone doesn't trigger an event, right? It's the groupings of these bins that aggregate to our project areas is what triggers alerts and triggers that process to go off. Then we can go out and send a dredge. We get more information and more numbers and metrics coming back from these dredge vessels to populate our bins with even more rich information associated with that, because we have various sensors on our dredging vessels. And then just to make sure we did our jobs right, and there's always some shifting around because channels are very dynamic places, we go out and send a post-survey vessel out to survey the channel again, just to make sure that we're still green and that channel looks good, right? Again, this is just an illustration of just one bin, but it's a grouping of bins, right? Very tiny bins through time. Then what we do is, on ingest, we calculate because of the whole volume and basic high school math stuff, we're able to calculate the what we call the shoaling rates, which is the rate at which a bin is going to pile up through time, right? So in this example, this particular bin is shoaling at a rate of 2.6 feet per year. So we can either project that forward if we've collected a survey very recently and want to know what that channel is going to look like in 6 months, or if we haven't collected a survey in 6 months, we can project it forward to today to see what the channel may be like today, and a dredging manager can then make a decision based upon that. So again, our AIS data that we backfilled with is constantly filling these groupings of bins, right? I've showed the unique identifiers here. These are the globally unique identifiers for the resolution 13 bins that we're using. So this AIS data that's driving over our bins constantly is constantly giving us that feedback loop and informing the bins of the sort of baseball card-like stats that are going into feeding these attributes, right? So we end up with a plethora of data to make a decision upon. And this is sort of another visual showing a cargo vessel going through our bins. So you can see at this resolution, you can barely even tell they're bins, right? But if the real-world vessel dimensions that we're going to have in our AIS data, we're actually working on implementing this now, would act just like this visual, right? Like we'd have a little polygon driving through the channel, essentially. And anytime it intersects with one of these bins, well, guess what? That's a problem. That could trigger an alert. We can add some draft, like if a vessel is coming through a channel and it drafts at, say, 30 feet down deep into the water, we could pad that with a couple of feet of underkill clearance, and we can use that as sort of like the safety protocol, right? It's like, hey, we want to know about a problem before it actually becomes a bottom strike or anything severe like that, right? So this is all in the name of keeping our channels open, and I believe the coin has been tossed around that these bins sort of act like our data integration framework at the core. And I believe it has the ability to be just that, right? Bringing all types of different data together to sort of study and understand the large picture a little better in our world. So with that, this is my contact information. And special thanks to our Wolpert and Bowhead partners for helping us develop this over the years. And I will be the guy in the Ask Me Anything and demo booth asking folks like Michael Young lots of questions about stuff, and come see me. Be glad to talk to you. So I appreciate everybody's time.